Um, all right, so let me, I guess, introduce Asim. It's my pleasure to introduce Asim. He is my colleague at IBM Research Center in New York. He leads many efforts, including reasoning, planning, and agentic workflows in enterprise-scale large language models. He has over 15 years of experience in AI and more than a decade of experience at IBM Research. He's led multiple leadership roles, including managing and being a program director for Neuro-Symbolic AI. He earned his PhD from Hokkaido University, Japan, and has authored over 80 peer-reviewed publications and is an inventor of 20 plus US patents. He also serves at advisory board for the National Center for Artificial Intelligence in Pakistan and Central AI Institute in the US. Please join me in welcoming Asim.
Thank you, Shireen. Thank you to all the organizers for inviting me also. So I would talk about reasoning with large language models and how neuro-symbolic AI agents can help solve some of the problems. And I'll go through some of the slides very quickly because I believe the community is already aware of some of the limitations we face with reasoning when it comes to reasoning with large language models. And I'll share some pointers, what we are doing at IBM and how you can also join the effort. Because IBM, one of the things we are doing is to keep a lot of things open source, where the community can actively contribute. Okay. So I always start with this. So when the only tool you have is a hammer, every problem looks like a nail. So I believe LLMs are today's hammer. So every problem starts looking like next token prediction, which is not true in most of the cases, right? So we need to have some kind of assurities if we want to make claims on intelligence and reasoning planning, and that does not come from LLM alone. So let me talk about reasoning with large language models and challenges. One thing that is super funny about large language model, it just give false claims with a lot of confidence. You just don't know when they're like very confidently giving you the wrong data. And also it's not only about how they reason or whether they can reason. It's fundamentally, I believe the word reasoning has also changed its meaning over past 2-3 years. Before large language models, we mostly used to talk about formal reasoning, where it was mathematical, logical reasoning, very symbolic manipulators or solvers with guarantees. Now we talk more about natural language reasoning. The other formal reasoning is still there. It's not gone anywhere. It's just that we are more interested. We suddenly became more interested in natural language reasoning, right? And we understand that reasoning and knowledge. So knowledge draws from previous experience, and reasoning can infer from kind of even missing information. It can look for clues in external systems also. Reasoning, of course, tells a story behind the scene. It helps with the explainability. Knowledge, on the other hand, just labels the scene. For example, if you see an image, knowledge can tell you this is a car, this is a tree, and stuff like that. Reasoning can tell you, okay, the car hit the tree or something like that, right? So, and then it comes like when we talk about emergent property, this was an early discussion in large language model, whether reasoning an emergent property of large language models or not. But now we understand some of it might be true, but it's also there are a lot of artifacts on how we evaluate reasoning. For example, when it comes to math or arithmetic reasoning, we don't have a continuous way of evaluating benchmarks. We have either two-digit manipulation or arithmetic operators, or we suddenly go to three-digit. We don't have 2.1-digit operators. So suddenly we see that the LLMs cannot do three-digit addition, three-digit multiplication, and then after a particular threshold, they start doing that. And similarly, in other domains also, we see this emergent property appearing. Is it emergent or not? You can find papers in both areas. And then we already saw chain of thought multiple times talked about in the session today. So we have like very fancy chain of thoughts. Self-consistency works very well. Even today, it's one of the best methods to produce very good results. Tree of thought, if we have if we have trained verifiers, we can do like advanced method like tree of thought, best of n, Monte Carlo rollout, and stuff like that. So can LLMs reason? So we know that large language models can deceive human evaluators, at least by fooling them with a very good natural language style and talking as if they know everything they're talking about. So so human evaluators get fooled by the style, but what about other kind of evaluation, the benchmarks? And we know that benchmarks can also be deceived, or there are artifacts in the benchmark. For example, like MCQs are evaluated, like even if we give a wrong answer, there is still a chance that 25% or something chance that it will be a correct answer. So there are artifacts there. One issue with reasoning problems are that we want, unlike other natural language tasks like summarization or rewriting a text, in reasoning we want 100% accuracy. For example, if I give you a calculator and I tell you it's 80% of the time correct, like how useful will it be for you, right? And what if I say I have improved the accuracy of this calculator, now it's 95% accurate? What will be the use of that calculator, right? So reasoning is a kind of, it's unlike summarization. Summarization, you can, it's a subjective task, right? Reasoning, on the other hand, is not subjective. It's either correct or wrong, just like a calculator. So there are many potential confounders where we can see that large language models struggle. There is a window in front of my, okay, it's not on the screen. So many potential confounders, like, for example, like I call it benchmark hacking. And this is one of the reasons why I didn't put any results in later in my slides, because it used to take like up to a decade to solve a benchmark, but now it's just a matter of weeks before we see like almost saturation in some of the benchmarks. Because we have the ability to kind of hack benchmarks also, but at the same time, on this figure, on the right hand side figure, we can see that as we go to a reasoning focused task, the LLM performance is still much lower than when we go to the retrieval focused task, which LLMs actually do very well. They are retrieval systems, right? Very, very complex, very efficient memory retrieval systems. And this paper also, I believe, like GSM symbolic, probably all of you have seen it. Like if we add some facts in our questions that are not related to the question, it significantly decreases the performance of large language models on reasoning tasks. For example, if there is a simple arithmetic GSM 8K like task and we add some information that has nothing to do with our question, the performance suddenly decreases. We would think that the reasoning models will not do that. Reasoning models will behave still sensibly, but actually their performance also decreases significantly. And for some model, up to 65 points decrease in performance. So all that make us think, like, if we want to apply large language models to enterprise systems, how do we do that, right? And that is where we can surely will go towards neuro-symbolic AI, and we'll go towards agentic systems. So in this, like, system 1, system 2, kind of like from this book, Thinking Fast and Slow, system 1 are the tasks that we do almost without effort, like it's kind of mostly retrieval kind of task. And system 2 are the tasks where we need explicit reasoning. They are usually slow. So no matter what we say, large language models tend to do system 1 tasks very well. System 2, they always struggle to do the slow thinking process. Although we claim that large reasoning models are much better, which they are, but still they have kind of same limitation at another threshold. And I asked, for example, even from a reasoning point of view, like I asked a large language model to create an image where we need both system 1 and system 2. And this is what it created, which is correct. It's doing driving, like the person is doing driving, which is kind of system 1 task, and doing math, which is kind of system 2. But it should not be done in this way ever, right? So there are limitations on what LLMs can do even now. This is pretty recent, like 6 months back. So as I said, so we think that large reasoning models solve the problem on their own, but actually they use a lot of tokens to make it a little bit better. That's how I believe what they're doing. So this is a simple question, and you can look at the reply that large reasoning model gives. So they tend to do, large reasoning models tend to do system 2 tasks a little bit better with a lot of thinking tokens. And thinking tokens simply means like we are giving them more quota at inference time to generate a lot more token than before coming up with the final answer. Some of the models share these tokens. OpenAI never shared the thinking tokens with us. And we have to go towards symbolic AI, but we understand that it's brittle and it comes with a lot of problems, right? So what is the solution? So we understand that large language models struggle with planning, multi-step reasoning, like just the grounding of facts. But at the same time, we know the strengths of large language models also. They are amazing at converting formats from, for example, natural language to code. They can call tools. They act as orchestrator, judge. They tend to be amazing judge when we give, let's suppose, two outputs and we ask which one is better, summarizing validation. So why do we expect, when large language models cannot do, for example, math, why do we expect them to be any better at math conversion tasks, right? For example, converting math to code problem. And the issue is, like, some kind of learning is just easier than other kind of learning. we cannot expect large language model to solve math on its own, but we can expect large language model to convert math into input for calculator. Okay, math problem into a proper input expression for calculator tool. So that's how we should be using large language models. And yeah, so the problem with uh, today's system is, or what we want the system to look like is, we want it to learn with a lot less data and cost. We want it to be human auditable, controllable, and the generalization issue that was discussed earlier also, we want it to generalize a lot better than what it can do on today's with today's system. So Neuro-Symbolic AI, if you look at this Gartner graph, in 2023, it was somewhere here where it says that it's around 10 years away from the peak, high peak. In 2024, it was 5 to 10 years. So it's very quickly moving towards the top. And LLMs kind of help Neuro-Symbolic AI a lot because of all that interface with the natural language that it can provide is super powerful, and that was not possible before large language models, really. So you have that symbolic domain, but humans don't like to talk in symbolic uh, domain, right? So we want to talk in natural language, and LLMs help us convert that into something that neuro-symbolic systems can pick. So this is like a taxonomy of neuro-symbolic systems. Yeah, I hope the video will be shared. You can look into more different ways, but basically the idea here is that either the controller is symbolic or the controller is neural, and the leaves can either be neural or symbolic or vice versa, or both systems can work together. Um, Sometimes they are differentiable, like symbolic systems are also differentiable. So, and there are different tools that are available that follow one or more of these patterns at the same time. So why do LLMs still work for natural language, but they don't work for some other kind of problem? And that brings us to manifold hypothesis, where we, although vision, language are very high dimensional problems, they lie on a manifold in that in a continuous manifold in that high dimensional space. For example, if we have a database of faces, like faces have some features that lie on some kind of manifold, like eyes, mouth, and skin color, hairs, and stuff like that, right? On the other hand, some discrete problems don't follow that manifold hypothesis, like even traveling salesman problem, constraint vehicle routing problem, uh, such kind of optimization problem don't, like hard constraint, anything with hard constraint does not follow this manifold hypothesis. So we cannot expect large language models to do very well on those domains. So here are like the ones where manifold hypothesis works, and the ones where uh, the manifold hypothesis just doesn't work. And right now, the way people deal with this problem is to kind of increase the number of parameters that large language model has. Just stretch, it's like stretching the space. Of course, if it's like very sharp peaks, if you stretch it, it becomes smoother, and then you train that, right? That's the way to do it right now. But we know that it has its limitations. We cannot keep stretching forever. We cannot have infinite number of parameters or infinite amount of data. So this is what neuro-symbolic system is doing. It's transitioning between symbolic and neural whenever one gets stuck, or it's not that easy. Like it's very difficult to even find out that one of the system got stuck. But for example, in kind of agents, the neural system keeps calling the tools which are symbolic, or we can have an orchestrator that is symbolic and it calls neural networks or large language models. So we can have this neuro-symbolic system very, very efficient with the help of agents these days. So these are like some of the architectures that I just mentioned. Either have a symbolic controller that is calling large language models, or large language models calling some symbolic tools, or some kind of sandwich architecture. And this, so we can see some of the tools that are available to us that follow one or more of these architectures now. But this actually brings us to agents. Like, this is what agents is all about: how to combine symbolic systems with large language models. And in my opinion, agents are one of the best ways to do neuro-symbolic AI these days. It just helps us transition between symbolic and neural domain seamlessly, and gives control to one of them. As we know, agents can either be fully like large language model based, where large language model acts as an orchestrator, or it can be an agentic workflow where we define the workflow in a kind of symbolic way, and we let large language models do some of the things, for example, judge or validate whether the output is good or not. And there is no limitation really of agentic architectures. There are probably gazillions of architectures. We can start with simple reflection, where the agent just try to improve its own output. We go to React, where we have reasoning, action mixed up, and so on and so forth. So there is no limitation, like, really, on how many agentic architectures exist, and for good reasons. Like, all of them solves the problem in one domain or the other. So the problem, like, few months back, I was searching for something, and I tried to build a small agent to help with my search, web agent, and on the back it was using a frontier model, and I ran just one query, and it ended costing me like $7 or something. Okay, so one web search for one shopping object, like I wanted to buy a laptop or something, and it did help a little bit, but it costed too much for a single query. $7 is ridiculous, right? So big models are not the solution to agents. So we are slowly moving towards how we can make smaller models work better in agentic workflows. So we understand that agents, in kind of like, when we talk about agents, the large language model have very specific tasks to do. We don't want large language model that is very general. Actually, it's sometimes, for bigger models, it's very difficult to, for example, know its own limitations. Large language model, like a very big frontier model, sometimes are very bad at saying that I don't know this information, or I need to refer to some other information. Smaller models that are purposefully trained on, for example, relevance tasks, are much better at saying that, okay, I don't know this, I have to go to another node to find that information. Large language models are inefficient controllers. We cannot expect just prompting a big model, very complex prompt, and expecting it to perform very well. It will be slow, very costly, and it will be very unstable, unpredictable in the loops. For one query, it might take 1 hour and like tens of dollars. For other query, it might just finish in one iteration. That's not the kind of behavior we want from our agentic systems, right? Yeah, so what we are working on, what my team is working on, how we can make small models much better in agentic workflows. So we definitely need specialized models for that. We have to train models for orchestration, for tool calling, and we introduce explicit systems. So the simplest architecture you can have is LLM and tools, right? So you have LLM that acts as your agent orchestrator, and you give it various kind of tools and have no workflow whatsoever. But that's not what we do. We do create an agentic workflow where we have explicit points in our flow where the memory gets summarized, where some of the validators get called, where some of the guards get called. So we work more towards agentic workflow, not very, very general agents. And by you may think that I will build an agent, and as the models keep improving all the time, my agent will also keep improving with the model. That's not how it happens. There is a diminishing return after, like, you make your agent work. Maybe with the next model it will improve few points, but you cannot expect significant jump in the performance of your agent. So there are several papers, few of them, like especially NVIDIA is going big on making small models work in agentic workflow. We are also working in the same area of making smaller models work in agentic workflow. And this is our, as I said, I explicitly, because putting too much numbers on the screen doesn't mean much these days. Large language models kind of can hack benchmarks very easily. So I'll share a few of the things that we are looking into, and I will have some links on the slides to the papers or to the repos that you can look at, or you can reach out to me. So for example, like what we are doing is we run the agent, we make a simple agent first, we run it with on some benchmark, some domain, we get the traces, we might assign some rewards, all the logs. We do some error analysis where we cluster similar errors together, and that those errors give us an idea how to improve this problem. Either, like right now it's a semi-autonomous process where a human needs to get involved. Ideally some of the errors can be done completely autonomously, where the agent figure out how to fix it the best way. So we really have few options of how we can improve it. We either can generate more data and train the agent in the current architecture, or we can add a new node in the agent and train a new model. Okay. Or we can adjust the prompt of the existing model. So there are a few options that we can do to make our agent better. So we decide that, and then we either, if the decision is to train a new component and put in the agent architecture, so we do that, and we usually train LoRa's. I'll show you why. And we evaluate again, and then evaluate both, like all the regression tasks and domain specific tasks that we want to do, the task that we trained our system for. And we keep updating this agent graph, and over time it keeps improving the performance in a very predictable and a systematic way on the particular domain, which might not be what the public like model or frontier models are good at. So it might be some enterprise problem that is hidden from the public view, right? And right now we are working towards building an end-to-end agent alignment system also, that is still under work. So I did not put it in this architecture. So few technologies that we use, one is activated LoRa. Activated LoRa is different than standard LoRa, where we train different LoRa's, and each LoRa has to compute its own KV cache when it executes. So in the right-hand side figure, we see, as we know, like the inference stage has two sub phases, like prefill phase and the decode or generate phase. So when we use the standard LoRa, we do prefill for first LoRa, and then we do generation for first LoRa, prefill for second LoRa, then we do generation for second LoRa. So this is how normal flow looks like. On activated LoRa, what we can do is that we can keep using the same KV cache. We can just use the base model, and at the proper time we can invoke the LoRa number 1, and at a given time we can invoke LoRa number 2. Okay, so we don't have to do all that KV cache computation again, which makes it very efficient. This is available on the archive paper. If you want to look into more, if you want to discuss more, feel free to reach out. And the other is Melia, which is a generative programming library that IBM is working on. Of course, this is open source. Anyone can contribute. And this basically, what it does is that it makes large language model a key component in programming language. Okay. Brings a lot of large language model, as we know it. We just control it by a prompt, and we expect it to behave properly, which it sometimes does not. So Melia just brings a lot of predictability and kind of engineering methodology to all that. It follows this instruct, validate, repair. I put a code snippet also on the right, where you can see that we can separate, instead of giving one long prompt to large language model where we say in one system prompt, do this, validate. Okay, that's funny. So validate this. We can have multiple requirements. For example, call one tool only. If there is no tool, this is the output format you should follow, and so on and so forth. We can break it down into multiple requirements. We can break our instruction down, and we can give it the repair strategies, how to recover from it. So this is what is provided by Melia, and at the same time, it provides very easy interface with, for example, MCP, agent to agent, or other kind of protocols. So Melia.ai, I'll highly suggest you to visit this also, and if you want, like, become a contributor too. So large language models can do reasoning in some capacity, but there are fundamental limitations. There are, like, one of the biggest limitation is the way we just evaluate the large language model reasoning. Neuro-Symbolic AI can help improve, and agents are one of the best way to do Neuro-Symbolic AI these days. It might change. Small models are necessary to make agents practical to use. Otherwise, as I said, so one query can cost like a lot of money. And also, if the orchestrator is so slow and the orchestrator needs to be called tens of times during an agentic workflow, it just doesn't make any sense. We want our orchestrator to be extremely fast and decide what next to do. If it's suboptimal, the agent will recover from it, right? But we don't want it to be very heavy, time consuming, too many tokens, too much thinking going on. All that does not make sense when it comes to agent. The purpose of agent is to make mistake, reflect on it, improve it, do something else, but do it very quickly. So what we are doing is, like, developing a framework to iteratively improve agent based on the evaluation, in a very informed way. Purpose build LoRa models, and then use the LoRa framework to make it very efficient in inference. So we have already seen that purpose build LoRa's, we can improve the tau bench, for example, BFCL v3, better than the frontier models by just adding few components. For example, one of the component that is very important we found is to check whether the tool call should be, whether there should be a tool call or no tool call. Okay. So instead of directly asking the agent to make a tool call, if you check whether tool call should even be done or not, that helps a lot, especially on BFCL, where there is a special category of relevance, irrelevance. It helps a lot. And Milia just gives the structure to everything that you're doing. It brings a lot of predictability, and it kind of feels like you feel more control over what you're doing. You can replace some of the components that are very vague. For example, instead of asking large language model that all the output should be in capital letters, you can very easily add a symbolic check in the middle in Melia, and it will just start doing that. So thank you. And just I put this, like I some of the things that I talked about you can find on my YouTube channel also. I made some videos about the agents and Neuro-Symbolic AI that I talked about. If you want, feel free to join the channel, and any suggestions are also welcome.
Thank you very much. Questions?
Asim, many thanks for such a great presentation. Very informative. I just wanted to ask you about evaluation, right? You didn't say a lot about this. What's your view about what the future looks like in terms of evaluating this kind of systems? Especially in the light of wanting more automation.
Yeah, evaluation is actually a big problem right now. So when I was working with reasoning only, not agentic system, I was fed up with MCQ evaluation all the time, right? So agentic evaluation make it a bit better, but for example, like in BFCL V3, which is one of the very famous, the issue is that you feel that you are doing actual evaluation on an actual agent, but it's there are no real tools running on the back, right? TauBench tried to make it a little bit better, but there are now two agents that are running. Like there is a user agent running, there is a agent LLM running. Okay, user LLM running is, it becomes very difficult to find out what error is happening at what stage. And that is why, like, the error analysis box in the figure that I showed is very complex. Like where the error is originating, it's right now we are not able to exactly pinpoint that problem. So I believe one of the things is that we have to create a lot of gym environments on that can give us
benchmark.
Benchmarks that can tell us, by executing the real tools, that can tell us what is going on at what point. Unfortunately, a lot of those still a lot of agentic benchmarks just give you the final one reward, average reward or something, one number, and that number is useless. Like there is absolutely, until it can give you a detailed analysis of what happened, I'll never touch that benchmark, even if it gives me just one number. So it remains a big problem.
Thank you very much.
Yeah. Thank you for such an insightful presentation, sir. But there's a question, like I am currently presenting a paper in which I am processing the noisy and the unclear context which the user gave. I would like to have your recommendation on the fact that when the humans are highly unambiguous and there is sarcasm involved, then how do you believe we can have that incorporated? Like the symbolic layer would be effective, or then we can proceed with the previous neural network aspect of it?
So that like ambiguity have to be dealt, like the large language model has to deal with that ambiguity. But as I said, so if you in math question in GSM 8K, which I believe you must be aware of, GSM 8K. If you add a fact that has nothing to do with your question, if you ask LLM to evaluate, it will usually mess up. But if you ask LLM to write a code to solve that problem, it can deal with that ambiguity a lot better.
Yes.
Okay. So the ambiguity has to be taken care of by large language model. It has to extract that fact. One of the video in the Neuro-Symbolic AI series, one of the video deals with that problem. You can check that, but LLM has to take that responsibility.
Like, I have an idea. Let's connect over it after the meet.
Sure.
Thank you.
Any other questions?